Welcome guys to this new video. Today we're going to talk about functions. I'm sure that this is a notion that you have met already in previous classes, calculus, etc. But this time we will describe functions with the language of relations that we have already studied. This means that you are going to describe functions as subsets of a certain Cartesian product. So let me start from the definition that you would find if you were Googling a function in the web. Probably your definition would look something like this one. A function is a relation between two sets that associates to every element of a first set exactly one element of the second set. So in this definition, I want to highlight three things. The first one is the word relation here. And then you see, this relation has two specific properties. It associates to every element, so every is the second word that I want to highlight here. Every element of a first set, exactly one element of the second set. So exactly one element here. So we will see that this every will be kind of our first property, and you will understand this better later, while exactly one will be a second property that a function has to satisfy as a relation. And when we have something like that, we can denote our function, we can write that f is a function from A to B. Well, A, with respect to the above definition, is the first set, while B is the second set, and f associates to every element x, so if x is an element of A, it associates to x an element y in B, which I can also denote f of x in order to highlight that y comes from x. So let me start from a straightforward example where we work with very easy sets. For instance, in this example, I'm going to take A to be equal to the set x1, x2, and x3, while B is going to be y1, y2, and y3. Okay? And now I'm going to represent a function between A and B in a geometrical way. So if A is this diagram represented by this ellipse, and B is this other diagram. So now what I have to do here, I have to put in A and B the elements. So in A, I put x1, x2, and x3, while in B, I'm going to put y1, y2, and y3. And now, in order to define this function, basically, I have to say where each element of A goes. So x1, I'm going to send it to y1. x2, I'm going also to send it to y2. And finally, x3, I'm going to send it to y3. So why this, let's say this diagram corresponds to a function? Well, basically here the two properties that I highlighted before are satisfied because these two properties put together are saying that for every element in A, there is exactly one arrow which is starting from there. And this is exactly the case here. Of course, we don't have to care about the fact that there is an element in B from which is not the landing point of any arrow. So this doesn't is not a property that we are asking for a function. So if we want to do some considerations here, we have that y1 can be written as f of x1, but also as f of x2. We have also that y3 is equal to f of x3. And if we want to say that basically y2 is not the landing arrow of any, is not the landing point of any arrow, we can write that for all x in A, y2 is different from f of x. Okay, so before giving a more formal definition, I want to show in this example how we can interpret this function as a relation, it as a subset of a Cartesian product. Of course, here the Cartesian product we are talking about is A cross B. So I want to define F as a subset of A cross B. Well, I can say that F is the set of ordered pairs xy in A cross B, and I'm just asking that y is equal to f of x, okay? An important thing here is the following one. So from what we can see here, we are saying basically that all functions are relations. So all functions are relations. But the converse is not true. Not all relations are functions, but not all relations are functions. And so now in the next page, basically we're going to understand why. Basically, in order to have a function, we need a relation with two specific properties. And I'm going to make some comments about these properties. Okay, so here is the definition. A function from A to B is a relation f from A to B such that, so 1 and 2. First thing we are asking is that the domain of f, and when I say the domain of f, I mean the domain as a relation. So the domain of f has to be equal to A. Second thing, we are asking that if xy belongs to f and xz belongs to f, then y is equal to z. And this corresponds exactly to 1 and 2 that I wrote in the initial definition of a function. Why? Well, 1 is basically saying that from every x, there is at least an arrow which starts from there, from every x in A. The second property is saying that I cannot have two different arrows that starts from a same element x. Basically, if I can find two arrows between x and two elements of B, y, and z, well, those two elements have to be the same, so that actually I'm talking about a same arrow. Okay, I want to give here some additional notation and terminology. So, notation and terminology. Okay, as I said, we denote f in this way from A to B. So we read f is a function from A to B, or also we can say that f maps A to B. The set B is called codomain. So B is called codomain of F. Then in the case where domain and codomain are the same, so if A is equal to B, we say that F is a function on A. And if xy is an element of f, so now we are considering ordered pairs because we are looking at f as a relation. So we write y equal f of x. And also we say that y is the image or also value of f at x, and x is a pre-image of y. Okay, so if we have an ordered pair xy, we say that y is the image of f at x, and we say that x is a pre-image of y. So here is very important to highlight these different articles, the determinate articles and undeterminate articles, because when x is given, y is unique. While if we start from y, it is not sure. First of all, it's not sure that we can find a pre-image. And on top of that, we don't know if this pre-image is unique. So this justifies here the different article that we use for the image and for a pre-image. Okay, so let me make this smaller and do a quick example here. So if let me see. So if I have a diagram here, A, and another diagram here, B. So here I have A, and here I have my B. So in B, I'm just going to put an element just to show a little bit x1, x2. Just to highlight a little bit more this last thing I was saying. As you can say, y here is the image of f at x1 and x2. While x1 and x2 are two different pre-images. So x1 and x2 are two different pre-images of y. Okay, so let me do an example here, where a more interesting example. So let's start from a relation. So in my case, R is a relation on the set of real numbers. So here, R is the set of ordered pairs where each coordinate is a real number. And I require that y is equal to x squared plus 3. Okay, so this here is what defines basically my relation. Okay, so what I want to show is that, so we'll prove that R is a function on R. Okay? So here, in particular, my A and B is equal R. Okay? So my function is a function f from R to R. Okay, so for sure, my function is already defined as a relation. So now what I have to do is to prove the property 1 and the property 2. Okay, property 1 was asking that the domain of the relation, so in this case of R, is equal to the set, in this case, to the starting set. So in this case, the set of real numbers. And then my property 2, I have to prove that if xy belongs to my relation R and xz belongs also to R, then I want to prove that y is equal to z. Okay, let's do let's do the first point. Okay, again, let's do this by double inclusion. Of course, the domain of R is contained in the set of real numbers. So this is trivial by definition. Well, now I want to show that for every real number, this is in the domain of my relation. So let x be a real number. I want to prove that there exists a y in R, so in a real number y, such that xy is in my relation. Okay? So define yx, this is just to put the dependence on x, to be equal to x squared plus 3. Then we have that xy, which basically is equal in this case x squared plus 3, is in R, because the second coordinates satisfies the fact of being the square plus 3 of the first one. Okay, now we have to deal with the second point. So here, again, remember, we have our assumptions. So we're assuming that, actually, let me do like this. X, Y, and XZ are in R. So these are the assumptions here. And now we want to prove the conclusion, which is this one. Okay, how do we do this? So assume that xy and xz are both in our relation. From the definition of the relation, this tells me that the second coordinate, it is equal to the square of the first one plus 3. So I can write that y is equal to x squared plus 3, and also z is equal to x squared plus 3. But given x squared plus 3 is a fixed quantity. So from there, I get that that y is equal to 3, that y is equal to z, which is exactly the conclusion I was looking for. So this way I proved the two properties for a relation to be a function, so that I proved that my relation R, in this case, is a function. Okay, so a first question for you. So I'm asking here, I'm going to list 3 different relations from A to B, where A is 1 to 3 and B is equal 4, 5, 6, 7. I want you to tell me which one is actually a function on A. So R equal 1, 4 to 5, S equal 1, 7 to 6, 3, 7, or T equal 1, 4 to 5, 3, 6, 1, 7. So 10 seconds for thinking about this. Okay, so I'm going to answer this question from a geometrical point of view so that we can understand better. So if I'm drawing my relation R, so I will have here my set A and my set B. So 1, 2, and 3. And in B I will have 4, 5, 6, and 7. And here I'm saying that 1 goes to 4 and 2 goes to 5. Then for S, I'm going to have, sorry if these ellipses are not beautiful, from A to B, again, 1, 2, 3, 1, 4, 5, 6, and 7. And here I'm linking 1 and 7, and then I'm linking 2 and 6, and then I'm linking 3 and 7. And in the last example, in the last case, I have again A and B, 1, 2, 3, 4, 5, 6, 7. And here 1 is linked to 4, 2 is linked to 5, 3 is linked to 6, and 1 is linked to 7. So I'm going to start by saying which one are not functions and why. So the first one is not a function because from 3 I do not have any arrow that starts from. Okay, so this is violating the first property, while the red one is violating the second properties, because from 1 I have 2 different errors. So 1 to 4 and 1 to 7. So here I have that 1, 4 and 1, 7 belongs both to R, but from there the conclusion that 4 is equal to 7 is false. Okay, so I'm violating the second property. So, and I can check that S is actually a function because it satisfies both property. In the specific, from each element of A, I have a unique arrow. So here the answer is S. Okay, so the next thing to talk about is the range of a function. Basically, the range of a function is the same as the range of a relation, but let's give the definition again. Definition. So let f from A to B be a function. So the range of f is defined to be the range of f as a relation which means that the range of f is equal. Remember, the range of a relation is the set of all the second coordinates of pairs of your relation. So in this case, I'm going to take the y in B such that there exists x in A such that xy belongs to f. And you can rewrite also in the following way. Is the set of y, element y in B such that there exists x in A such that y is equal f of x. This is the range that you have always studied in calculus, just reformulated in a different way with the language again of relations. So a first remark, of course, also in this case, the range of f is contained in B. But now, while the domain has to be exactly A, this inclusion can be strict. So this is not, but it is not equal to B in general. Okay. So this is an open question now. So I'm asking, what is the range of the following function on R? So my function is the set of ordered pairs xy such that y is equal to x squared plus 3. So I suggest here to stop the video and try to work the example by yourself before watching the solution. So 10 seconds before answering. Okay, so here what we have to notice is that x squared for every real number x is greater or equal than 0. So this suggests us that actually y has to be greater or equal than 3. So we have a lower bound on y, but we do not have any upper bound. So my intuition here tells me that the range of this function f is equal to 3, to the interval 3 infinity. But now we have to prove it. So again, we need to do two different inclusions. So first of all, we're going to prove that the range of f is contained in 3 infinity. So as always, let y be an element of the range of f. So this implies that by the definition of range, that there exists x in R such that xy belongs to f. But since xy belongs to f, this gives a condition, the second coordinates y, which is y equal x squared plus 3. And now I'm going to use the fact that x squared is greater or equal than 0. So here I can say that I'm using x squared greater or equal than 0. And so I get that this is greater or equal than 3, which basically proves that y is an element in the interval 3 infinity, 3 included. Let's do now the other containment. So this time we're going to take an element in the interval 3 infinity. So this tells us that y is greater or equal than 3. And now we have to prove basically that there exists an x such that y can be written as x squared plus 3. So first of all, from y greater or equal than 3, we also understand, this implies that y minus 3 is greater or equal than 0. And when I have a real number which is greater or equal than 0, I can define its square root. So if here we set x to be equal to the square root of y minus 3, okay, we could have also set x to be equal to negative the square root of y minus 3. This is also a real number. And so we have now that x, y, which is in this case square root of y minus 3y, belongs to R. Why? Because if I take the first coordinate, so square root of y minus 3, and I do y squared plus 3, you can easily check that this is equal to y. Okay, so last thing before leaving you is we're going to talk about real functions. These are particular examples of function where the domain and the codomain are subset of the set of real numbers. So let me just write this. So real functions are functions whose domain and codomain are subset of R. Okay, let's do a first example. Consider R to be equal the set of ordered pairs xy in R squared such that y is equal 1 over x. Okay, I'm saying here that R defines a function But now I have to be careful on the domain from R minus 0 to R. So this is important here because if I do not remove 0, this is not a function since 0 would not have an output. No, 1 over 0 would not be defined. So here what I'm saying is that the domain is equal to R minus 0. The codomain here is equal to R, okay, because this is the landing set basically. But the range now is strictly contained in the domain because it is equal to R minus 0. Okay, I'm not going to prove this formally, but I want just to give you an intuition because here we're working in the real plane, so we can basically represent the graph of this function. So let's work in the real plane. So this is my x-axis, this is my y-axis. Okay. So I have x and y, and now remember, here what we want to do basically is to represent the function y equal 1 over x, right? And here, if you remember, this function looks something like this. So again, remember when you want to find the range of a relation, what you're looking is the projection of your graph on the y-axis. And so here, basically, if we do that, let me highlight here. So if I color this in red, and now I'm going to do here you will get, when you do this projection, all the real numbers apart 0. And you can prove this formally if you want. So now I'll end this this lecture about functions with a true and false or false question. So here we consider the relation given by xy in R squared such that x is equal to 4y squared. And I'm asking, is basically, if I say R with domain 0 infinity is a function from 0 infinity to R, is this statement true or false? So 10 seconds for thinking about it. Well, okay, I don't know if you were slightly confused because this can look as a parabola. Actually, it is a parabola. It's just not the parabola we are always used to because it's a parabola which is rotate of 90 degrees. So if let's start from a geometrical point of view. So if we draw here our axis, so the y-axis and the x-axis, well, you can see here what we want to represent is basically, I'm not going to say the function, but the curve, which is associates to the equation x equal to y squared. For instance, for y equals 0, I get 0. So 0, 0 is on the curve. For y equal 1, I get x equal 4, okay? So if, let's say like this. But for y equal negative 1, I get also, for y equal 1, I get x equal 4, which is here, and more or less. And for y equal negative 1, I get, let's write here, 4, negative 1, and 1, and so on. So this is a parabola. You can keep finding points if you want. And so already we said here that for 1 and for negative 1 belongs both to R. So there are two ordered pairs with the same x coordinate, but this does not imply that 1 is equal -1. So 1, but 1 is different from -1. So we are violating the second property of a function. And this basically you can see with what you have always done before with a vertical line test, because you can find a vertical line that intersects the curve here in two different points. And so this is not a relation, so this answer is false. And with this, we conclude the first introduction to functions where we have described them as relations. So thank you all for the attention, and see you in the next video.